Hi, my name is Felix Brandt, and I will present a joint paper with Florian Brandl, Dominik Peters, and Christian Stricker. And the title of the paper is Distribution Rules under Dichotomous Preferences. So let me start with a concrete application of our model, donor coordination. And one specific example where this could be useful is the Amazon Smile program. I'm sure that many of you are familiar with this. So Amazon allows customers to select a charity from a list of charities provided by Amazon. And whenever you purchase a product from the Amazon website, then 0.5% of the price of this product are donated to this charity. The point of departure for our model is that it seems fair to assume that customers actually have preferences over charities and not only favor a single one. So let's not go all the way to ordinal or even cardinal preferences, but just assume that customers are equally happy with several charities. So we would allow for customers to approve more than one charity, and then Amazon could cleverly distribute the contribution of each customer among his approved charities by taking into account the information provided by the other customers. So let's look at a concrete example here. So let's assume we have one customer who approves charities A and B. So that doesn't mean that that his money should be equally divided between A and B, but just that he's equally happy for every dollar that is donated to either A or B. And then there's another customer who approves charities B and C. Then any efficient distribution rule would donate both contributions to B because it would recognize the mutual interest that both customers have in charity B. So both customers are actually happier than without coordination, which would presumably just split their contributions evenly between their approved charities, because the charities approved by the customers receive strictly more money. So Amazon Smile is just one example where this could be helpful. So the Italian revenue agency's Cinque per Mille program is another example. So this program allows citizens to divert 0.5% of their income tax to a non-profit organization of their choice. And other examples include classic charity matching programs, such as those that are offered by big companies, for example, Microsoft or Apple. So it seems obvious that coordination can be beneficial, but that leaves the problem of which distribution rule should actually be used. And our paper is concerned with the axiomatic study of distribution rules. So for example, here's a minimal requirement that we could impose on distribution rules. In order to incentivize customers to participate in the Smile program, Amazon should donate money to at least one approved charity of each customer. Okay, so that seems like a reasonable minimal assumption because, for example, we would not want that all money goes to the most popular charity, because if you're not a fan of this charity, then there's no benefit for participating in this program. So our main theorem shows that no rule that satisfies this minimal requirement can simultaneously satisfy efficiency and strategic proofness. And this impossibility holds despite the fact that we only have very simple approval or so-called dichotomous preferences. The theorem confirms a conjecture by Bogomolnoyer, Moulin, and Storm from 2005. And actually much of the model that we study is based on this classic paper that I will refer to BMS 2005 in the following. So let's look at our general model. So we are concerned with the divisible and homogeneous resource that we want to allocate among a set of public projects. Okay, so this resource could be money, as in the donor coordination example. It could also be time or probability. So for instance, probabilistic social choice with dichotomous preferences can be modeled as a special case of our setting. Now, each agent contributes some amount of the resource to a common pool, and the sum of all of these contributions is called the endowment. Furthermore, agents approve a non-empty subset of projects, AI, and then we have a distribution rule, F, that allocates the entire endowment on the projects. Okay, and since we only have dichotomous preferences, the utility functions of the agents are defined very easily, because the utility of an agent is just identical to the amount of resources that is spent on projects approved by these agents. For simplicity, we will assume for most of the talk that all the individual contributions are actually identical. So for most of the talk, the CIs will also be identical and equal to 1. Okay, now let's look at 3 typical axioms that we can impose on distribution rules: efficiency, strategy proofness, and positive share. So the first ones are classic economic axioms. So efficiency just means there is no other distribution such that all agents get at least as much utility and one agent is strictly better off. Strategy proofness means that no agent benefits from insincerely stating which projects he actually likes. And positive share merely means that the utility of each agent is positive. So for every agent, at least some tiny amount of the resource is spent on projects approved by this agent. Okay, so now we have 3 axioms. And now let's look at 3 typical rules for this setting. The first one is the utilitarian rule, and that one distributes the endowment uniformly over most approved projects. So we have an example here, and the way to read these tables is as follows. So we have 5 agents, and we have 4 different projects, and the gray boxes denote which projects are approved by which agent. So the first agent approves projects A and C, and the second agent approves projects A and D, and so on. And in these examples, the contribution will be identical for all the agents. It's always equal to 1. And now it turns out that project A is most popular. It's approved 3 times, whereas the other projects are just approved 2 times. So the entire endowment of 5 will be spent on the first project A. Okay. Second, we have the conditional utilitarian rule, which is an interesting variant of the utilitarian rule proposed by Dadi in 2015 and further studied by Aziz, Bogomolnoyer, and Moulin in 2019. So here the idea is that the contribution of each agent is spent entirely on projects that he likes, and namely those projects that are most approved by the other agents. So the first 2 agents still put all of their contribution on project A because it's the most popular one. Now the contribution of agent 3 has to be spent on projects that he approves, which would be projects B and C. Now B and C are equally popular because they're approved by 2 agents each. So the contribution of agent 3 will be split evenly between projects B and C. And similarly, the contribution of agent 4 will be split evenly between agents B and D. And finally, the contribution of agent 5 will be spent entirely on project A because that's the only project that he approves. So the distribution returned by the conditional utilitarian rule is to put 3 on A, 1 on B, and 0.5 on C and D each. Okay, and the third rule that we look at is the Nash product rule. And I'm sure that many of you have heard about this one before. So the Nash product rule returns a distribution that maximizes the product of agents' utilities. So this is not so easy to verify manually. You have to trust me that in the example that I'm showing you, there's a unique Nash product distribution, and that is to put amount 3 of the resources to project A and 2 on B. So now if we compare these 3 rules in terms of the axioms, it turns out that the utilitarian rule clearly violates positive share, right? Because agents 3 and 4 both receive a utility of 0, which violates positive share. The conditional utilitarian rule, on the other hand, satisfies positive share, but it violates efficiency. So there's another distribution for this particular example where all the agents receive at least as much utility and one of them is strictly better off. And this distribution is to put 3.5 on A and 1.5 on B and nothing on C and D. Okay, so if you imagine 3.5 on A and 1.5 on B, then the utilities of the first 4 agents are exactly the same, but the utility of the last agent will be 3.5, so it's strictly more. So in general, for this preference profile, it's the case that any amount that is split evenly on C and D can be moved to A and B in order to improve efficiency. So in these cases, we say that the sub-support CD is Pareto dominated. Okay, so the Nash product rule satisfies positive share, and it also satisfies efficiency, but unfortunately, it violates strategy proofness. So that's not the case for this example, but you can construct examples where the Nash rule violates strategy proofness, and that was actually done first by BMS in 2005. So in a nutshell, we have 3 different rules, and we have 3 axioms, and each of the rules violates exactly one of the axioms. And that, of course, begs the question whether there is a rule that satisfies all 3 of these axioms. And as I have mentioned already, our theorem shows that this is not the case whenever we have at least 4 projects and at least 6 agents, and those bounds are tight. So this theorem strengthens existing theorems by BMS and by Duddy. So those theorems by them used much stronger notions of positive share or strategy proofness and additional axioms such as anonymity and neutrality. And somewhat surprisingly, our proof actually goes through with a much weaker notion of strategy proofness than the one that I have just defined. So the notion of strategy proofness that we need requires that a manipulator has to enforce that the entire endowment is distributed on his approved projects. So in other words, a manipulation only counts as a manipulation if the manipulator gets maximal utility by misrepresenting his preferences. So let's have a look at how this proof looks like. So essentially the proof is a list of preference profiles. So here we have a first profile. So we have 6 agents and 4 different projects, and those here are the approval sets. And how the axioms impose certain restrictions on which projects can actually receive a positive amount of money. And our proof only considers the supports of distributions. So we do not care how much of the resources actually spent on a project. We only need to know whether it's a positive amount or not. So we are only interested in the support of a distribution. And here, for instance, positive share implies that B and C have to be in the support. And then additionally, efficiency imposes some restrictions. So for instance, here, the sub-support AD is dominated by BC. So similarly to the example that I've shown you before. And therefore, there are only 3 possible supports in this particular example. And here we make a case distinction and assume that the distribution puts positive amount of resources on BC or ABC. And then we construct another preference profile in which agent 3 changes his preferences. This changes the implications by efficiency because now, for instance, project A is Pareto dominated by project C, so we get a different set of possible supports. But we are not done yet, so we will construct a much longer sequence of supports for this proof. So we go from one profile to another. There's always one agent who changes his preferences in order to get a different outcome. And we heavily used computer-aided tools, most importantly at SAT-Solver, to get this proof. We are now almost done with the first case. And then we can look at the second case. So this not only required a considerable effort by the computer, but also by my co-authors, Christian and Dominik. So we couldn't obtain this proof by just exhaustive search. We had to come up with a lot of clever techniques in order to eventually get this proof. And finally, the proof uses 386 profiles, and then we get a contradiction to what supposedly was selected in profile number 1. And we have reasons to believe that there are no significantly simpler proofs for this statement, which actually shows why this statement was open for such a long time. Interestingly, we did find a much simpler proof when additionally assuming anonymity and neutrality. And the proof that we found for this statement actually only uses 2 different profiles, but the statement is still stronger than the theorems by BMS and Duddy that I mentioned earlier. So that's quite fascinating because this 2-profile proof we could have found by ourselves, but we didn't, and neither did BMS or Duddy, which I think emphasizes the usefulness of computer-aided theorem proving in general. All right, now, in the interest of time, I will go over the remaining results of the paper quite quickly. So we studied a couple of other axioms. So one of them, for instance, is called decomposability. And you may have noticed that for some of the rules, such as cut, the distribution can be split into individual distributions, such that every agent only spends his own money on approved projects. So this does not work for util, but it's important when the contributions are actually owned by the agents, and the mechanism only gives recommendations how to spend them. Okay, so this is formalized in the decomposability axiom. And in our paper, we show that decomposability is actually equivalent to another axiom that has been proposed in the BMS paper called group fair share. So it's a classic fairness axiom. And we showed that these 2 axioms are equivalent using the max-flow min-cut theorem. Now, other properties that we looked at are participation incentives, which are also quite interesting in this context. So clearly, we would want agents to be better off by participating than not participating. And this property is formalized using a strict inequality here because agents not only bring their preferences to the table, but also their contribution. So they are contributing an additional amount of resources. So it seems natural to assume that the utility should be strictly larger for participating than to not participating. And actually, this property can be strengthened to what we call contribution incentive compatibility, which says that your utility for participating should be at least as large than for not participating and spending your own contribution on approved projects by yourself. Okay, so CI is the contribution of agent I. So contribution incentive compatibility is obviously stronger than participation, and both of these axioms imply positive share. And then what we did in the paper is mainly that we conducted a thorough axiomatic comparison of distribution rules. And not all of the results that are shown in this table are actually new, but we did propose a new rule, the sequential utilitarian rule, SUT, which to the best of our knowledge is the first rule known to satisfy efficiency, monotonicity, and positive share. And it even satisfies decomposability. So this last column here shows our impossibility result. So there's no rule that satisfies efficiency, positive share, and strategy proofness. And maybe one other thing that is noteworthy is that for all of these dashes and check marks, actually proving that this is the case is in some cases quite difficult. So for instance, showing that the Nash rule satisfies contribution incentive compatibility requires a very complicated proof, which is actually the main result of another paper. And for instance, showing that the sequential utilitarian rule violates participation required us to construct a manual counterexample using 45 agents. So that would be this dash here. So coming back to the donor coordination problem and Amazon Smile in particular, we think that, for instance, the conditional utilitarian rule seems like a prudent choice. So it can be easily explained and satisfies a large number of desirable properties. Okay, so thanks very much for your attention, and we'll be happy to answer any questions you might have.